Hello. Welcome to the ISSS session on computational physics with Python. And I hope that it has been a good experience for you till now. So we will be starting from where we left off from last day. And sorry for starting a little bit late. I got a little bit stuck up with preparing dinner for the night. So yeah, but nevertheless, thanks for understanding, and also thank you for bearing with the trouble of starting 15 minutes late. But I hope that I will be able to cover up for this, and we'll be able to cover adequate amount of stuff in the next 2 hours. Okay, so let us get started. So we are in assignment 2, solving the question. So we'll start from question number 5 because we left off at question number 4 last day. So okay, so let us get started. So let me first share my screen. Yeah, I hope my screen share is on and it is visible to everyone. So let me switch back to the question. So here the question says is that the biochemical process of glycolysis, the breakdown of glucose in the body to release energy, can be modeled by the equations. The two equations are given. Here X and Y represent concentrations of two chemicals, ADP and F6P, and A and B are positive constants. One of the important features of the nonlinear. Oh, okay. So one thing to clarify here is that today most of the questions, in fact, all of the questions, I guess, are on different ways of solving transcendental equations. So what are transcendental equations? Well, say you have an equation where generally you have an unknown and you are required to solve for that unknown. So the some transcendental equations are some particular type of equations for which you cannot directly analytically solve for the unknown quantity. And then you have to resort to numerical methods for solving this. So one example of transcendental equation is say x minus sine of x, right? Or x equals to sine x. So now you need to find at what values of x is this equation satisfied. And turns out there is no direct analytic way of really figuring out the values of x for which this condition is satisfied. And such equations are known as transcendental equations. For example, if you have an equation like 3x plus 5 equals to 9. So this is not a transcendental equation because you can clearly say that so x equals to 4/3 because 9 minus 5 is 4, and so 3x equals to 4, so x equals to 4/3. So you do not need any numerical technique for solving this. This is analytically solvable. But generally speaking, for transcendental equations are those special type of equations for which we cannot solve analytically. And therefore, we need to devise some sort of a numerical technique for solving these types of equations, right? So this is mainly the idea, okay? So you see, okay. Let me go back to the chat. I think something had happened in here. And let me once again reshare my screen. Okay. Yeah, I think my screen is now visible. Okay. Right. So this is one sort of set of transcendental equations. So one of the features of the nonlinear equations like these is their stationary point. So I'm coming back to the question. Okay. So with which the derivatives of both become zero simultaneously, so that the variables stop changing to and become constant with time. So these are called stationary points. So stationary points would mean that the values of x and y do not change with time. And that would mean that the dx dy and sorry, dx dt and dy dt both are equals to 0. And if both of them are equals to 0, then what you can do is you can rearrange these equations to solve for the values of x and y. And you can show here that if you use these two sets of equations and make dx dy, dx dt and dy dt both equals to 0, you can write analytically that x equals to b and y equals to b over a plus b square, right? This is simple, and I hope that you guys would be able to do it. I give you like around a few minutes to figure this out, and then please let me know, and then we can proceed. Okay, so just set dx dt equals to 0 and dy dt equals to 0, and then we can try to rearrange the equations so that you get x equals to b and y equals to b over a plus b square. Solve, like you have two equations and two unknowns, and then solve for them. Basically, is the idea. Yeah, let me know if there is some problem with this. I'll just like wait for 2-3 minutes for you to figure this out, and then I will proceed. Is there any doubt? Otherwise, we can like proceed to the next part of this question. And so there it says that show that the equations can be rearranged to read this. So for getting to the second part, what you do in here is you know that x equals to b. So everywhere where there is b, you can replace it with x. And if you do that, then what you will have is y equals to y times a plus x square is equals to x, right? Because like in the second part where y equals to b over a plus b square, if you know that x equals to b, then you can replace the b's with x, that you will get the first one on the left hand side, which is y times a plus x square equals to x, right? And similarly, uh, you can also get y equals to b over a plus x square, where you just replace the denominator with x, because again, you know that b and x are equal. Okay, so these are the two equations here it is given, and then it says that write a program to solve for these stationary points using relaxation method with a equals to 1 and b equals to 2. You should find that the method fails to converge to a solution in this case. So let's talk about what is the relaxation method. So in the relaxation method, what you do is you keep on, say you have a value of x, right? And then you have a value of y. So you keep on iterating through the value. So say you start with a value of some guess value, right? Say x equals to 1 and y equals to 1, just as a guess. And then you keep on repeating this, and hopefully you will come to a solution. So let me demonstrate this. So what this would mean is that, say you know this formula, which is given in here, x equals to y times a plus x square, right? This is the formula that is given, right? So what you do every time is that you're starting with some initial value. You say this is xn plus 1. By n plus 1, I mean the value at the next iteration. You keep on iterating, right? You start with xn, which is the yn, sorry, and xn, right? So this is kind of what you do. And then after you have got this value, you use the new value of xn and yn, like xn plus 1 and yn plus 1, and substitute those in place of xn and yn to get xn plus 2. And you do the same thing for y as well. And hopefully after a few steps, you are going to converge to the solution. So that is the idea of relaxation method. So let's try to then write the two functions, right? So the first function is x, right? So we will write x equals to bda lambda x comma y. So these are the two things which we are taking in, and that is equals to y times a plus x squared, right? And I think I have already discussed about lambda functions before. We do not know a and b for sure here. So a equals to 1 and b equals to 2. So let's write that. A equals to 1 and b equals to 2, right? So this is one function which we are defining, a function of x and y, where oi times a plus x squared. So lambda function is what I have already covered in the previous class. And the idea here is that when you write lambda, this x comma y, this is same as writing def x comma y colon. And then you are writing return of this. So this part is the same as this part. Just that writing it in this way makes it quite simple and in one line instead of two lines. So that's the only advantage. Okay. So right. So let's we have written this x y times a plus x square, right? And then we write y equals to y times a plus x square lambda x comma y b over a plus x star 2 x squared, right? So now we have defined these two. So now what we are going to do is iterate through. So for that, I'll just give something like a max iter equals to 1000. This gives me maximum iterations. And then we will have something called tolerance, which say 1.0 e minus 0.6. So what this would mean is that when we keep on iterating through and we see that the values of x and y do not change between one iteration to the other iteration by the value of by 10 to the minus 6. So the change between the two is below 10 to the minus 6. Then we know for sure that here we have reached the required amount of tolerance and the solution has converged. So that is what tolerance means. And maximum iter is like total number of iterations. So irrespective of how much is the tolerance, if we see that the total number of iterations that we have done is above the maximum iterations, then we will say that, okay, we have not converged and we have reached our maximum limitation of doing something. So if our max iteration is very large, then in case of non-convergence, the code will take like a very long time, which we do not want. So we give a reasonable value of 1000 in here. Okay. So let's now try this. So we do a while, right? And we do something like difference. So diff is like the difference in values. So np.inf. We start with some random value, which is infinite. So we do while if is greater than tolerance. So we will keep on looping through and improving, guessing our solution or trying to find a solution when something like when our difference is greater than tolerance and iterations is less than max underscore iter, right? And to start with, our iterations is 0, right? Because we have not iterated. So these are the two conditions which we are using And now let's go to the next step where we do something like here we are going to guess, right? So we also give start with x val equals to say 1 and y val is equals to say 1.5. This is some random values which I'm putting in. It can be anything. Just for this example, I'm putting this in. Now I'm doing something like x new is equals to, we are going to call this x, and we will be passing x old and y old. Okay, so let's call this guess. GUESS, right? And we are defining, let's call this x old and y old. So this is what we start with, and we pass x old and y old in here to get x new. And similarly, y new is y, and we pass x old and y old, right? Okay, I have not defined numpy, so I'll just define that as usual. Okay, so now once I've got this, I will calculate the difference, which is the absolute value of x minus old minus x underscore new plus. So I want to have both of them to get together. So yeah, that will be, then let's add these two in quadrature, and similarly, let's not have the absolute thing in here, and similarly just doing this and putting this in a square root, right? So this is where we find out the value of x new and y new and try to find out the difference. And we then look at the thing and we say that, okay, if the difference is greater than tolerance, we'll keep on continuing. Otherwise, we just come out, right? And here, now we are going to print x new and y new, just to see what the solution we are getting, right? And if I run this, let's see what happens. To variable explorer and also remove all the variables which were previously there. This is from some of the code which I was writing. Let's restart the kernel. Let's wait until this finishes, and then we have a working Python terminal where we can run the code. Yeah, what's happening in here? Let's have a new console command plus plus. Okay. Yeah, something happened with this one. So let's try to run this in a different kernel. Okay. So I think we are stuck somewhere. And the place we are stuck is basically I have forgotten to increase the iterations plus equals to 1. So it's just stuck in an infinite loop because the question has said that things are not going to converge. Okay, so let's see what happens when I run this. Just remove the variables and let's run this code. And we see that it's still at 3 and 1, which is not ideal because the number of iterations is 1,000. As you can see in here, in here we have already reached 1,000 iterations. So this means that the variables are not, the solution is not converging, right? So this is exactly what the question says, that the solution does not converge. And if you print the values of x new and x old, you can really see what's happening. So, x old and y old. So let's print that. Print x old, y old. You can see that the values don't become very similar. They just keep on changing. So you see the values just keep on remaining the same 1.0, 1.5, something like this. So the solution is not converging. And this can be a generic case where things don't converge for these sorts of stuff. So you need to rearrange these equations. And let me go back to the questions that I have to tell you that what will be the rearranged form. So the reason for this is that you have to look for the derivatives of these equations close to the stationary point, like the d2, or in other words, you need to look for the second derivatives, which are going to tell you how things are going to look like close to the values where the things should are supposed to converge, right? And the values where it is supposed to converge is if your a is 1 and b is 2, then x equals to 1 and b equals to uh, 2, and then it should be, I think, 2 by 5. So 1 and 2 by 5 is where your things should have converged, but you see that that is not what is happening in here. So then let's try to see what's the rearranged form it should be. That I have this small PDF where I have written this rearranged form, and this behaves much better numerically. And we have seen other examples as well that what you get algebraically is always not the best choice when speaking of numerically solving a set of equations. For example, we saw this same thing in the case of one of the previous questions while dealing with roots of a quadratic equation. Then although both there were two different equations to choose from, and they were algebraically speaking at identical to one another in terms of what they mean, but since their forms are different, one of them can be better behaved in certain numerical conditions. So this is exactly what is happening in here. So we are going to change this. So we are going to change x equals to b by y minus a. So let's go back and change this to b by y minus a, and I think there is a square root as well. Yep. So mp dot sqrt. So the other thing to note in here is that these two equations, algebraically speaking, are the same as the previous one. You can look at it like it is just a rearranged form and nothing else. And y equals to x over a plus x square. Y equals to x over a plus x square. Right. So now once we have got this, let's see what is happening in here, and are we able to converge to a solution or not. And here you can see we converge to a solution where we have found out the values of x and y's, and we come to a solution in here. And does this solution look good? and you can also like check with the code in here that we are doing. And here you can see, similarly, we are checking this, and then we are trying to find out what is the values of X and Y. All right. And then we are looking for the new and old. We start with X equals to 1 and Y equals to 0. So let's see, X equals to 1 and Y equals to 0, and try to run this once again. Yeah, so we will get something like a divide by error because B by Y is there. So let's say 0.1, and let's see what's happening in here. Yeah, we can also like give a statement saying that things have not converged in here. This will be iterations. Then we will just get notice that it didn't converge, right? So minus, okay, so it's minus square root of this. And x by a plus x square. So g nu is x by a plus x square. So we have done this x by a plus x square, and this is b by y minus a. Let's call this f. Let's call this g. X equals to b by y minus a, and x by a plus x square. So x by a plus x square, and we take x and y's in here. So this makes it like a lambda function. But yeah, the other thing that we can do is perhaps get rid of the other stuff, but let's have it for the sake of similarity with the previous thing that we were doing, and check the difference in here. Hmm. How about trying the other way around? Still not converging. Oh, there is something else that I have also forgotten, right? Because I'm changing this to x new, and then I have to update it, right? I forgot the update. So x old. Now new is going to become the old one, right? And sorry, the old is now going to become the new one, because we have already used the old. So the old is going to become the new one. And similarly, y old is going to become y new. Got it. Okay. So now let's try to run this, and let's get rid of the minus sign and run this. And you see we are converging in here. It didn't converge come, and you see we start with 1 and 0.1. Some guess say this can be also 1.5, which we were trying previously, right? And then again give this, and you see that within 26 iterations, we converge to a solution where x equals to, roughly speaking, 2 and y equals to 0.4, right? So this is the solution that we come to. Okay, so let's print here. Right. So then let's try the previous one where we saw that things are not converging. So this is y times a plus x square. So we are going to comment this out and write it as y times a plus x star 2. And the other one was y times a plus x square and b by a plus x square. So b by a plus x square. And although, as you know, that for this specific case, this equation is analytically solvable. And when that we already know that we want x equals to 2 because x equals to b for for a equals to 1 and b equals to 2. We know that it's 2 by 5, y equals to 2 by 5, and x equals to 2 is the solution. So we are definitely converging to the right one, where this is close to 2 and this is close to 2 by 5. Right. Okay. So let's try to run this. And here you see that we are not able to converge to a solution. And we get to don't converge, and hence the solution, which is obviously the wrong solution, is this. Right. So we didn't converge and we get something like this, which is a problem. So, okay. But with the previous choice, which were a good choice of coordinates, we were able to get a solution which converged and get an answer to it. So this is the relaxation method. So please let me know if there are any problem or if you have confusion with something. So as usual, I am taking time so that there is absolutely no problem and no confusion before I move on to the next question. So please let me know. I will wait for a while. Yeah, since there are no questions, I think I can move on to the next one. It says that about the wind's displacement law. So Planck's radiation law tells us that the intensity of radiation per unit volume and per unit wavelength lambda from a black body is at a temperature T is this given by this formula, where h is the Planck's constant and c is the speed of light and kb is the Boltzmann constant. Write a program to calculate the wavelength lambda emitted by at which the emitted radiation is strongest. Solve the resulting equation to an accuracy of 10 to the minus 6 using the bisection method and find the value for the displacement constant. The wavelength of the maximum radiation obeys the Wien's law. So bisection method is also one of the methods for finding out the root of an expression or an equation of a transcendental equation and numerically. And the idea here is that about the root on either side of an equation, it changes sign, right? So what would that mean? So let's look if there is some helpful articles on bisection method that would be useful. This is bisection method of root finding. right? Okay. So the root finding algorithms work in a way that we want to find out the root where a function fx equals to 0. So the value of x where a function f as a function of x equals to 0. So let's see if I can write it in better way. So suppose we have a function fx equals to 0, and therefore we want to find out at what value of x is this condition satisfied. And then these values of x are known as the root of an equation. So bisection method tells you that if a root exists, which for example here you can see in this diagram, this red point is where the function fx equals to 0 because it hits the x-axis. So the value of the function is 0. So then you take 2 points, say a1 and b1, which are on two sides of the root. So if you see that at the true root, which is the red point, since this is 0, then to the left of it, it's the function is positive, and then to the right of it, excuse me, and then to the right of it, the function is negative. It can also be other way around, but the idea here is that on either side of the root, the function has a sign which is like which is opposite. So if it is positive on the left, then it is negative on the right, and vice versa. So then what you know is that if this is the case, then definitely the root of the function lies somewhere in between a1 and b1. So then you go halfway between a1 and b1, and this is called bisection. And then you check, so which is say a2, and then you check what is the sign of a2. If the sign of a2 is, oops, check what is the sign of a2. If the sign of a2 is like here, for example, is positive, which is opposite to sign of b1, then you replace your previous estimation of the left-hand position, which is a1 to a2. And then again, you compare a2 and b1, the signs of the function at a2 and b1. And then again, you see if the signs are uh, opposite, which you already have known, then you find out the value at halfway between a2 and b1, which is a3. Right? And then again, you do this. Then now you know that, okay, the solution lies somewhere between A3 and B1, right? And then you again make it half. So in this way, you proceed. So for example, A1 and B2, the half, I think, is somewhere here. So you have it, you first half it and you arrive at B2. And since the sign of B2 is same as sign of B1, you discard B1 and go to B2. And then you again look for the midway between the two, which is A2 in here. And then you look for the sign of A2. And if the sign of A2 is now same as sign of A of the function at A1, so you discard A1 and come here. And then again, you halve the two and come to A3. And in this way, as you do this again and again and again, you'll reach at a position where the values, like the A values, do not change as much. So then, or the B values, whatever be it, do not change as much. Then that would mean that you have come to your required amount of tolerance, and that is going to be the root of your solution. Okay, so this is how the bisection method works. So I hope that this is clear to you. So let's try to write a code which is going to work for this. But for that, first let's write the function, which is I lambda. So we want to find out the place where I lambda is largest. So that would mean that the place where d lambda is equals to 0. Okay, so that is going to be the function which is d lambda equals to 0, and the root of which we want to find out. So let's write I equals to dda lambda wave. This is the wavelength. And the tricky part here is that your thing is also lambda in here. So we will not write lambda because lambda already is a special keyword in Python. So we'll use write wave, which stands for wavelength. And then you have 2 pi hc square. So a couple of constants, so 2 times np dot pi times h times c, sorry, times h times c square. lambda to the power minus 5. So wavelength to the power of minus 5 divided by, within brackets, np dot exp of hc over lambda kbt h times c over wavelength times kb times t minus 1. Okay, so we have got this. So now obviously we do not c square, well, it's the times in here, right? And we now have to put in the constants. So h equals to something and c equals to 3. This I know, this is the speed of light in meters per second, but h, as far as I know, it's 6.626 e minus 34. This is h is the Planck's constant, right? And then we have something called temperature. So this is another variable t, which I'll put in here, which is temperature. And kb is the Boltzmann constant, which I have forgotten what the value is. So let's look at the value and copy it from Google. And this is Boltzmann constant. In SI units is what I want. Just copy this value blindly. Right. And just to be sure, I will also check the Planck's constant as well, since I'm already in here. 6.626 e minus 34. Yeah, I think I'm right in here. Okay, so this is this. So now we want to find out di dl, right, which is eta at some wavelength and some temperature is nothing but I. So we can use the wave plus delta minus I wave comma t, this and that thing, divided by delta. So this is approximation for, and let's have delta as 1.0 minus 0.3, something like this, right? So this is an approximation of a derivative, right? If you numerically want to find out derivative, this is the expression for a forward derivative, right? You can also do something like wave minus delta. This is a bit better in terms of the estimate. This is called central difference, which is a better estimation of the derivative. So you can also do this, right? And this gives you the derivative did lambda or did wavelength. Okay, so we want to find out a function where didl equals to 0, right? So the function f is equals to, this is again lambda. We pass in wave and some temperature T, right? Thus that we have EI, EL, wave, comma T, right? And we want this to be equals to 0. And that is where we want to find out the wave, at what wavelength does this become equals to 0 at different temperatures, right? So let's now take temperatures, right? And let's do np dot log space. We will take different temperatures, say from 4 to 6, 100 points, right? So then that what this means is that we will in log space we go from 10 to the 4 to 10 to the 6 with 100 points, and they are logarithmically spaced instead of lin spaced. Okay, and 4 to 6 is like 10 to the power 4 and 10 to the power of 6. Okay, so for every temperatures we are going to find this out, right? So now let's try to write the bisection method for this, and for that we are going to do a while loop, right? We are going to pick a C, which is the intermediate point, right? So A, B, and we are at every point A plus B by 2 will be our C. Okay, so this is the C, which is to start with, we have a dummy value and do a while. Similarly, we are going to have something called max iter equals to 1000. So again, we have something like a max iter, and we do something like while x old minus x new, or we call it difference, while def is greater than tolerance and iterations is less than max iter, right? And our def is np dot infinity to start with, right? So we go in and our iterations equals to 0. And here we come into this and try to find out something like a x old. So x old equals to, this is the guess value. So guess value is say 200. I mean, this is just something I'm giving it on my own. And now we do a F. We call it at some, oops, we call this at some wavelength x old and some temperature T, right? Okay, I have also not defined tolerance. E minus 0.6. It's my tolerance. And C is equals to 0. So C is, as I was saying, is the intermediate point, right? So now we do something like we have to also find given a like an estimate for A and B, right? So let's not have something like old, have something like A, which is say 10, and B, which is like 100,000, right? So it's like left and right, okay, is what we want. And generally the wavelengths are in what are known as angstroms. So, and 1 angstrom is like a 10 to the power minus 10 meters in SI. So we do something like just to convert this to angstroms, and C is for to start with is 0. Right now we do C equals to always A plus B. So we always bisect it. So this is where the bisection comes in. A plus B by 2, right? After we have bisected this, what we can do is now we will do an if condition. So we consider if the function f of A times f of B is greater than 0, right? F of A times, sorry, f of C. So we are going to compare C. So we know that if A and C are greater than 0, then that would mean that A and C have the same sign, right? Then A has to be replaced. So that we know A equals to C. Because they are of the same sign, then we replace this. So become A equals to C. And if they are of different signs, then the other one has to be replaced, which is B has to be replaced. So we do else B equals to C, right? The ones which are of same signs has to be replaced, while the one which are of different signs has to remain the same. And we will keep on doing this. And we now calculate the def here, which is np dot absolute value of f of like the value which we had, which is A minus f of C. Again, I think we can do a square root in here because we have two things to compare. So f of A minus f of C whole square plus f of B minus f of C whole square. This is the difference. And if differences become small, then you know that you are okay. And now if iterations is equals to max iter, you write print max iterations reached. So we have not converged actually in here in this specific case. And after this, we include the iterations plus equals to 1 because we have to increase it by 1, right? So we have to give some temperature to it, right? So you see F is called with some T, while here nothing is called with T. So we have to pass some temperature to it at all the calls to F. This is exactly what I'm doing in here, passing a temperature, right, to all the calls of F that are in here. And then I can do something like T, get this in a for loop for T in temperature. So this gives me something like this. I give a tab. And then there is this that you have reached the maximum number of iterations in here. Okay, so let's try to run this. It says invalid value has been encountered. Why is that so? Okay. So, okay, the one more thing is here. I also have to copy these. Otherwise, this will not work because at every temperature, I'm going to reset this. Okay. So let's also First, clear this up to this one. Try to debug the code. Get in here. Iterations A, B, C. Right. C equals J plus B by 2. So get some value of C. And then there is some A and T. So check this. So I get some invalid value. HC by lambda KBT. That is minus 1. 2 pi HC square times lambda to the power 2 pi HC squared times lambda to the power of minus 5. Yeah, I think I'm doing right. So where is this scalar divide? So this division is perhaps causing the problem. So what are we getting in temperatures? Let's see. There is one divide in here for sure. Stop this. And let's run this code. So it says that it's encountering some error in line number 39 and also line number 17, where it basically tries to find what is the wavelength. And yeah. This can also be written something like this, just because this is get the same thing in here. Let's see. Let's run the code once again. Let's run to the next breakpoint here. Now let's see. Let's see if the what I'm now going to do is just break it down into small parts, just to see where the problem is happening, right? So here, instead of wavelength, this will be A, because say I'm passing it to A. So let's write A. This part comes fine. And let's now look at the other denominator of it. So I'm just trying to figure out where the 0 is happening. This part is again A. This is also happening fine. So now let's see when I have both of them together. Sorry. A and I guess this is E. I'm having just something which makes sense. So I think the problem is with delta, most likely, because so let's write this one as 1 plus delta, because then this becomes comparable, right? And this is 1 minus delta, and there is a multiplication sign in here, right? And this just makes things fine, I guess. And then we yf plus delta yf, yeah. Okay, so let's try to see. Okay, let's stop the code, run it in here, tell this, try to see. Okay, now at least this part runs, right? And I have some value for the diff, which is pretty large. I go in here. Let's see, the diff is, yeah, you see that the diff is decreased to 2016. Let's see, it's now decreased to 349. Now 139, 64, 21, so 0.23, 10, 5, 2.5, 0.6, 3, 0.07, yeah, 0.009, I guess. Yeah, so I think we have gone quite a few iterations, 24 iterations or so. It's decreasing, obviously. Yeah, and we come out in here. Okay, I think we are good to go. So we can come out and stop the debugging. I think this code is now working fine. And here we now print temperatures because, sorry, here we print the, okay, so we have to have something as well. So max web is mp dot zeros. Like to start with is temperatures. So now here, after this, after the bisection has been done, we give the max underscore web. And again, I'm going to use the index, right? And the enumerate function, which again, we have covered in one of the previous classes, which you right, yeah, one of the previous classes, which just gives you the index as well as the value. So here I will give the index just to get the index of what the maximum value is. The maximum value is here is a plus b by 2. So a plus b by 2 is the maximum value that we are going to get. And then we can print max underscore wave. So this is the maximum wavelength. And we can divide it by E 1.0 E minus 10. This makes it in angstroms, right? Because it's better to have all the wavelengths expressed in angstroms, right? So that's what it is. And now let's try to run this. And you see, we get a bunch of like 1,000 different values for the lambda and the temperature, the maximum wavelength, right? So here we can now use a plot to see what the maximum wavelength is for a temp. And we can also do this for one particular temperature, right? So let's first test with, as the question says, for a temperature of 502 nanometers, right? So okay, which is the second part of it. So let's then try to do the first part where we try to do, okay, got it. The first part is just finding out this. So let's have numpy, sorry, matplotlib, matplotlib dot py plot splt. This is going to give us a plot. And now what we are going to plot in here is plt dot plot temp. So you see that on x-axis we are going to plot 1 over temperature, And on the y-axis, we can plot something like Maxwell, right? So this is going to give me the maximum wavelength, and the other is going to give me temperatures, right? And here, this is PLT dot show, right? And once I get this, let me open the plots and run this code. I get something which perhaps doesn't make sense. So what are the temperatures? Thing, say 2 to 8. So if it is a log plot, is it better? No. Let's check what we have, what I have done in the previous code. So this is 6. So you see I'm using the bisection method. My function is this one. Yeah, 4 to 6. Minus 6. I start with some t. So I define my delta as 10 and 10,000, right? I do it at 10 and 10,000. Okay, so I do it at, say, 10. And then what am I plotting? I'm plotting lambda max in terms of E minus 10 in terms of angstrom, and temperatures in terms of some kelvins. And let's see. I get something which is not expected. I should have got something like this. Lambda max in nanometers, and this is in kelvins. So nanometers, instead of nanometers, I'm just doing angstroms. So wavelength in T and delta is something. Minus 6. So probably I should have a delta which is even smaller to have something which is a better estimate. Okay. And the wavelength is, let's see, 7 to 9. So this is from 7 to 9 is what I tried in here. So let's try the same range from 7 to 9. Then it's 1 by T in Kelvin. And lambda max in angstroms. So the maximum wavelength is coming out to be something like this, and the night number of iterations is coming out to be this. Let's try to do this. Let's come back to this later and try to do the temperature of the sun for this, where we are going to find out the temperature where the lambda is given. So we are going to again use the same bisection method as before, but instead of having temperature lambda fixed, we are going to have the temperature fixed. Sorry, we are going to have the lambda fixed and find out the temperature in here. So the lambda is fixed to, so this will be T and this is going to be A. Sorry. So here, this is going to be WAV and this is going to be A. And this is going to be WAV C, B, and WAV C and WAV, right? So now this fixes the kind of the the wavelength, and we want to find out the temperature. So let's set WAV equals to, it says it's 502 nanometers, 502 times 1.0 E minus 0.9. So that's the definition of a nanometer, right? And we have this, and we are going to go through a few number of iterations. And after that, what I'm going to print in here is and this is a temperature is what we want to estimate. So we start from 1.0 E plus 0.4 10 to the 4 to 10 to the power 6 E plus 0.8, somewhere in between we know that the temperature should be, and then prove. So the print is T sun equals to, we can use the F string, A plus B by 2 is what the sun temperature of the sun is. Let's run this one. So we get something like this. So there are some problems which is happening with invalid value in subtract and scalar things. So I think that is what is causing the problem. So what we can also try to do is try to find out the derivative of this with respect to, okay, and we also have to find out then the derivative of this with, instead of lambda, with T, because it is the temperature which we the maximum. So yeah, so we want to find out the derivative, analytic form of the derivative instead of using a numerical approximation, and perhaps that will be better. Okay, so let's use Google for finding out the derivative. There is something called a derivative calculator. So we can use this one, or you can also, I mean, obviously calculate this yourself, but just for the sake of this, I am going to use this derivative calculator. -5 divided by exp of hc by bta lambda kb t -1, right? And here the entire thing should be in this, and then this is with respect to lambda, right? Is what we want to do, and we hit go just to get the result of this. We can simplify this. And here it is. So let's copy this one, and then we can use something like, and then we can edit this in Python, right? This will be np.py. This will be c cube. This is h squared. This is np.exp, right? This is just kb. This is web. So I'm just replacing it everywhere. This is now kb. Web to the power of 7. np.exp t times kb times web. This is to the power. This is again np.py. This is c squared. Web star star. This is np.exp kb, and then this is again web. -1. Okay, so let's try this one. or DIDL. Or DIDL equals to 10 to the minus 10. Okay, I think after I do the changes not in the space of in SI quantities, but I do the change in, yeah, I do the change in the quantities, which is, yeah. So let me then make this functions. I have to make this functions two-liner functions because I will have more than one lines in here so that I can manipulate stuffs. Then I'm going to have a return of this. Then I'm going to have wav equals to wav times 1.0 e minus 10 because I want this to be in units of, yes. Yeah, because I want this to be in units of angstroms, right? And want to work with angstroms. So yeah. Okay, so now this will help me just give something like this, something like a 1,000 and 100,000 angstrom, right? And hopefully clear this. So let me get through the code easily. And for temperatures, I will have temperatures equals to T times 1.0 E3, 03. Right. So this is again going to make things easy. And then so this will be then 3 to, sorry, 6. So let's see, come in here. Come in here. So we have a C, which is a plus b by 2. So let's see, C is initially 0 and a plus b by 2. So somewhere in between. Now let's see what diff is. Some value. Is the diff reducing? Does reduce. Just want to see what the value of diff does. Goes to how many iterations? I mean, 43 iterations. Suddenly, why does diff go to 0 here? So let's see. I want the A and C's to be as close as possible, right? So why am I using this? This is my error, mistake. So this is A minus C whole square plus B minus C whole square. So all this should be close to each other within 10 to the minus 6 is when I reach this. Okay. Now let me stop this, create the variables, and run this one again. Let's see, the def decreases quite rapidly. And then C and B is equals to C. So one thing also want to confirm in here is whether if A and FC start with opposite signs or not. If they are not, F A and FB, then it's a problem that we have not been able to bisect it. I mean, to start with, the initial guess is not on two different sides of the root, right? Yep. So let's see. So let's see what the value of A is. It's 1. And what's the value of B? Is this? So if A comma T is nan, B comma T is also nan. So should I move this to 100 and move this to 1000, 10,000, something like this, just to check why am I getting nans in here. Okay. Now what is F? Let's see. If I do something like I still get a nan. I think this is the one which is causing problem. Okay. Let's try this one. Stop the code. Let's just see what's the problem of the NAND thing, business that's going on in here. This is 100 angstrom. This is some temperature. And then let's see. This is 0. Why? Times f to the power of -5. Still 0. Two pi 8 c squared. Why is it 0? Oh, got it. What has happened in here? This C and this C overlapped and clashed. This is a really, really silly error. So this is C0. Let's call this C0. Let's call this C0. Wherever I have C's, this is DI, TL. Wherever I have C's, I will call it C0. C0s in here. And I guess now we are good. Let's stop the code, run this till the next one. Yeah. Now let's see if this makes sense. Yeah, I get something. I get something which is also negative. So this is not good then. I need to get something which is of the same stuff. Otherwise, yeah, problem. So let's see. Let me stop the code. Once again, try. It's a problem again. So let's try 1. Stop the code. Try again. This is no problem. So, okay. So now I think this is working because, let's see. This one and B, these are of opposite signs. So these are on two sides. Okay. So let's try to see if the diff is going to decrease or not. Yes, the diff is decreasing as usual. Okay. So let's stop this one and start to plot it. There are places where I have some problems. Okay. Let's not try to change the temperature. Okay. There are some problems which I see is happening in here, which we can try to solve the next day, I guess, because it's already a lot of time since we are trying to debug this. Unfortunately, we were not able to go till the next questions, but we are definitely going to solve this before we call it a day. Okay. So A equals to 1 and B equals to 1000. We go in here, convert the wavelength. Let's check, go the other way and see if we are able to use the previous method of calling I whatever plus. Okay, so let's see. Where am I calling a float object in here? Oh, this is, I missed the times. Times. Right. So let's see what magic did I do in here. So I used nanometers. Okay, let's see. Did I do something wrong in this formula of I? So what I'll do is I'll copy this one so that C0. Also, let's say speed of light is this value. Wavelength should be wave h times c b times t. Yep. So we'll not use this one as well. And let's see. Hmm. Trying to get rid of these. And so this is a problem in here. Is fixed. So let's try to copy this and see whether we are able to at least reproduce this or not. Then we will try to figure out what's happening. Right. Okay, this works. Here. So what I want to see in here is cons.c, cons.h, cons.c, here, cons.k. I think I have there is no problem in here at least. Let's see here what values do I get. Here I see, for example, the A is not changing. Right. So let's see, let's try this for some F, which is different. So F is equals to, say, 3x 3 times x minus 4. So 9. Right. So we know that this should be this should give me 3. And let's see, check if the bisection method here is giving me something which is we are not. So for that, I'm going to copy all this, come out in here, write something in here. Right. Okay. So I'll stop the code, start with an A, which is -8, and B, which is 20, and C is 0. And let's see. Move all the variables in the code. So I should get something which is 3. So there is no problem. And then come in here. So C is something. So it's 20 minus 8 will be 12, and half of 12 is 6. Come here. Check this. A changes now. So now the solution should be A plus B by 2, which is 3. So this works pretty well. And I don't know why it is not working with this. Okay, so I think we are way over time. So I'm going to call this a day. But since we have wasted, I mean, there has been a lot of time which we have spent in one question, we are not able to move on to the next one. So I think we will have one more extra class where we will be able to cover a substantial part of this next week. So I think that will be it for today's session. I will stop the share and we can go back to this. Okay, so the share has been stopped, and I hope that this was kind of a bumpy day today, but I hope that you were able to at least get something from it. And we will be resuming with one more extra class next time. So until then, uh, have a good night or good morning wherever you are. And let's just stop the recording.